Okay. So good morning, everyone, and welcome to Lecture 21 of ECE 3311, Principles of Communication Systems. And today's lecture, we're going to be focusing on two relatively important modulation schemes, QPSK and MPSK, or MPSK. So we're going to really be focusing on the phase modulations in today's lectures. But before we do that, just again, I didn't quite conclude in an adequate fashion lecture 20. So we're going to finish off lecture 20 first, and then we're going to jump into QPSK and MPSK. All right. So let's get started. So like with all other modulation schemes that we're dealing with in today's lecture, we're going again to the sort of basics, right? So we have the general expression for converting a message signal. In this case, it's digital. It's a digital message signal, and we're taking B bits, okay, which translates into one of M possible modulation waveforms that gets represented by a baseband signal every TS seconds, so every symbol period. And we convert that into an amplitude, phase, or frequency. As we'll see soon, we can actually take combinations of those. And what we do is we make a unique waveform, right? First in baseband, but then it gets modulated up to a passband frequency. And that is what gets communicated over the air to a receiver that will attempt to guess, well, I call it guess, but it really tries to detect what amplitude, what phase, and what frequency, right? Because as we'll see, we can make combinations of that. And we can try and figure out what the transmitter sent. And then from there, decode back to the binary pattern. Okay. So just like every other time, we'll go back to the general expression, right? This is very important. We always go back to the general expression. Passband waveform, S of t. And again, in some places I use V of t, but it's the same old thing, right? It is a signal that has non-zero components at carrier frequency plus and minus Fc. Okay, Fc hertz. We also do radians per second if it's omega c, and we have the relationship described here in equation 1. We have G of t, which is the baseband waveform, right? That's the mapping from a message signal, binary message signal, M of t, to some sort of waveform that has an amplitude, phase, or frequency, and that's going to be G of t. And that gets multiplied by e to the j omega c of t, or e to the j 2 pi fc of t. And that's the conversion process from some baseband, okay, the baseband signal, G of t, to a passband signal. And the real operator makes sure that we only get the real component of that, and that's our S of t. Okay? So from last time, if we want to recap, what we looked at is FSK. And we saw two flavors of FSK. We had discontinuous, okay, and we had continuous. Okay, the discontinuous was quite brutal. It was like, simply put, it's like it was a multiplexer switch, and depending on what value, okay, if it was a binary one, so it was binary FSK, depending on what value during that symbol period we had, it basically switched to one of two possible frequencies, right? So we had something like this for discontinuous. So depending if we had some phase angle, And what happened was, there's the box. That's our output. That's our mux multiplexer. And depending, okay, what our message signal is, right? We selected one of two possible frequencies, and that's what gets outputted at the end of the day. So we get something that looks pretty brutal, right? So we can either have a frequency like this, and then suppose that we had some sort of like, different signal, different frequency altogether. What we would have is something that would maybe start here very abruptly and higher frequency. And then let's say that's a binary 1. The red was a binary 0. And we just had these abrupt changes. Right? So kind of abrupt, kind of discontinuous, like really wasn't super great. But what we found with the continuous was a lot more elegant, a lot more graceful. Okay. So what we had there, right, is we definitely leveraged. So we had constant amplitude, right? df from minus infinity to t, message signal. Again, very careful because t is here. So d tau. Okay. So this enabled a much more smoother transition between F1 and F2. So what we get is same thing, binary 0, binary 1, let's say to binary 0. What happened is instead of like boom at every boundary of the like symbol, what would happen is, let's say this was a slow frequency, went to a faster frequency from 0 to 1. We would steadily increase the frequency until we reached, and then we would slow things down to get back. So let's say this was F1, that was F1, that's F2, that's F1 again. What we would have is this sort of transitional period where we would get here faster to go from F1 to F2 and slower. Perfect. That's great. Right? So that's great. So we had that was a lot more suitable solution. Then we looked into this horrible thing that was the PSD and the spectral lines, okay, of an FSK signal, and it looked really messy, right? And now what happens is we're switching gears again, and we're now looking at detectors. So how do you decode, okay, in this case, for an FSK signal? So just like we had modulation schemes, we also have demodulation schemes, right? So there's one. So there are two. So one is coherent. So coherent, what this means, what this implies is that we must have some sort of reference signal to both the frequencies, right, F1, F2, and phase. Okay. So in this case, the coherent detector looked like this. So in came, my passband signal. And the first thing I would do is I would demodulate. So I would use cosine 2 pi f1 of t. And then I would have, just leave it at that. And here I would have cosine 2 pi f2 of t. You might say, okay, I could do that. Mind you, this guy is still at fc, and you know there are variants, right? You could first of all demodulate down to passband, or sorry, to baseband, and all you have is g of t. You could do that. You could also operate this at passband. It depends on whether you have the components or not. But the goal here, okay, the goal here is to bring that to a low pass filter. So so you could do that. No, wait, no, let me double check, because FSK, yeah. So what you could so what you could do is, if you do this, right, the critical element here is F1 and F2. So what you want to do is you want to bring this thing down, right? So now, if you do that, what do you have? So what you do is, if you bring if you multiply, you get some, and you apply to trig identity. What you should have somewhere in there, okay, is you're going to have some sort of signal that's going to be at DC, right? Or what should happen is you should have a signal at FC. So it depends on what you have. So in this case, what might make sense, okay, is even before you do this, in my case, like what I'm thinking, if I want to use a low pass filter here, what do? Well, this may or may not work, right? Actually, it won't work like that, because with a low pass filter, because if you do that, what are you doing? Well, what you're doing is you're taking, let's say, that signal. So let's go back. So you still have this guy here. This is kind of pesky, because you're still operating at FC. So you can't use a low pass filter. You're going to have to use a band pass filter to extract out whatever's at FC. So one thing you could do, okay, is you can modulate this thing up. So first of all, bring it down, instead of FC, bring it down to G of T. All right. So what you could do before you do that is what? Is the following. So what you would do is, let's say you take S of T. Okay. You bring it down to baseband, right? But baseband is still relative, because you have these two deltas, one at minus F1 and one at F1, right? That's the cosine function. So the first thing you want to do is bring your signal down from whatever the carrier frequency is, down to baseband, and then you want to filter that out, okay, to one of the two possible carrier frequencies, right? F1 or F2. So you're going to take this guy and you bandpass filter that. So that's going to give you G of T, or G of M of T. Now the goal here is you're going to take that G of T, right? And you want to filter, and you want to now figure out, what is G of T? Is it F1 or F2? So now what you want to do is you now run that. So let's say if this was discontinuous FSK. So what is G of T possible being? Well, G of T can either be cos 2 pi F1 of T, or cos 2 pi F2 of T, okay? So what happens if we do this process? So suppose I set this guy, just for example. So what happens if I multiply cos and cos? Well, that's great, because then we apply that and the trig identity. So at this point, this is going to be equal to what? So it's going to be cos A plus B plus cos A minus B. Okay, and each one's a half. So it's going to be the following. It's going to be equal to half, right? And it's going to, and since the arguments are 0, we could have a pesky phase term. And I think what I did here with the discontinuous is I did have a phase term. So let's put it in just for completeness. So let's say we had a pesky phase term, but that's constant. So what we would have at the end of the day is we would have this, okay, plus half, and we would have a double frequency term, right? We would have 4 pi f1 t, okay, sorry, and there would be a cos there. And then the low pass filter would only produce this guy here. How about this end? This end, not as good, right? This end would be what? So this would be, this here is cos A minus B. Here, let's say we do the same thing. It would be cos 2 pi f1 of t. Let's say it's 2 pi f2 of t. So subtract that. And interesting. Sorry, I am really bad today. So if these are identical phases, this would be cos of 0. That would be 1. Huh. Even better. Actually, even way better. So this would be 1/2. Perfect. Perfectamundo. So here we would have that. And here we would have double. It doesn't matter. That term is going to get factored out. So here, what we would have would be half cos 2 pi f1 of t plus, okay? And if this difference, if we choose f1 and f2, okay, to be somewhat large and the low pass filter to be sufficiently narrow, all of those are going to get filtered out. So first of all, let's get rid of that. It's really going to just be half. And this is beautiful, because then what happens is, what we do is we pass these values. That's plus, that's minus. And then we have a decision-making device, okay? So is it a positive value? Is it a negative value? What happens is, if we have chosen this instead, rather than the top, we would actually have a positive value down this branch at the end of the day, and that would have been 0, the top branch, and it would be producing a negative value. So at the output, okay, here, we would either have a positive value or a negative value. If it's a positive value, okay, it's going to be f1. If it's a negative value, it would be f2. So that's how the coherent detector, right, coherent modulation for PSK would work. So what it would do, but very importantly, we would have to have a reference signal here. We would have to have a reference signal here. Obviously, we would have to demodulate down to baseband, to G of t, what these things are, right? So what we would have had to have done is bring all of this down, okay, to DC, okay, and then do the demodulation process there, okay, or at least, okay, or at least some frequency. This is if you don't want to mess around with pesky, like, you know, high, like really like bandpass filters with very high kind of like frequencies where the allowable frequencies are allowed to pass through and then band reject everything else. So this is one way of doing that, okay? Alternatively, you can also do non-coherent detection. So a detector of FSK, and this is non-coherent, okay, is you can do the following. You take the signal, and what you do is you filter out, bandpass filter, okay? This could be at F1, this can be F2. So what happens is, across every TS seconds, the main thing here is you have to check every TS seconds. Is there a value, is there a value, is there a value popping out at the output of each bandpass filter? And so what happens is it yes or no? And what you do is, once you're done, okay, once you have, so every TS second, so I'm going to emphasize that, every symbol, okay, what you do is you do an envelope detector. Okay. So what ends up happening is, so what happens? What's the output? Well, here, you're only going to get some sort of sinusoidal signal at F1, right? Here, you're going to get a sinusoidal signal at F2. But what we want to do is we want to extract the value. So what happens is, if there's nothing, okay, so let's say there's no, at TS, like at some time value, what happens is it's either or. We're not going to get something at both F1 and F2. If something is at F1, the other one's going to be 0. And something is at F2, the other one's going to be 0, right? And what the envelope detector does is it takes the sinusoid and turns it into some sort of constant voltage level. Remember, in this case, information is only encoded into frequency. So the amplitude should be equal to a constant. So the envelope detector, what's going to do? So remember how an envelope detector, the reason why it's non-coherent is we absolutely do not depend on any sort of cosines of any frequencies or phases. We don't have to know in advance what the phase or frequency is. So all you do is you filter out, you get that sinusoidal signal. You take the square of it. That means it's a sinusoidal signal. You take the square, you're going to have a DC term and a double frequency term. You'll low pass filter out the DC term. So you keep the DC term. You get rid of the double frequency term. You square root it. And now you have a constant value. And it too goes into a decision-making device, right? You take the sum. So very importantly, you either add or subtract, whether it's upper branch for F1 or lower branch for F2. So if something got sent on F1, it's going to be a positive value because the lower branch is going to be equal to 0 because there's nothing there. Likewise, if something was sent on F2, the branch above is going to be 0 because there's nothing up there. So what ends up happening is that you either get every TS seconds either a positive value, so plus sign VE is my shorthand for positive, or a negative value. So every TS, right? Every symbol, period. And then you have a decision-making device, just like with a coherent detector. Decision. And that tells you whether it was a 1 or a 0. Okay? So that's the end. That was the end of lecture 20. I just wanted to go over that because I felt that, well, first of all, I ran out of time and I was kind of fumbling through. But this is how detection for FSK works. In the case of non-coherent detection, you extract out, right? And here too, you can either play at passband, right? Or you can demodulate down to baseband or some signal in between, but you have to know where F1 and F2 is in order to pull this off. Because ultimately what you need to do is bandpass filter out that signal, envelope detect to give you a constant, and put it through the decision-making device. All right? Okay. So this is the biggie. So it's one of the biggies. So what we're going to be looking at is the PSKs. Okay. And we talked a little bit about BPSK, and this was kind of important. But now let's really go into the PSKs. So the PSKs, the way they work is the same like we've always played with them before. Let me derive, okay? So PSK modulation. So PSK modulation, and this applies, I should have started just forget about BPSK and just like do all the PSKs in one shot, but what the hey. So remember, we take our general expression, Schneikes. And what do we do? Well, what do we know about this? What's our, for a phase modulation, so PM. So our mapping, G of M of T, that's going to be equal to AC, some sort of amplitude constant. No information is communicated that way in this case. E to the J, okay, D, and then it's equal to that. Where theta is equal to dP M of T. It's a straight shot. It is completely 100% a straight shot in terms of like, well, basically whatever our message signal is, our map, our information gets like is multiplied by this phase constant, and that's what is equal to theta D. Now, to get the complete expression without that like real operator, right? What do we do? Well, it's going to be equal to this. So if we replace G of M of T with the definition for it, it would be equal to this. Okay. Now apply Euler. So S of T is now equal to AC cosine mu 2 pi FC of T plus, okay. What we could do, we can generalize this a bit. So let's say we just keep this plus, I'm going to include some non-idealities, okay? So this here, we know it's a phase modulation, so we do this. This is a constant. This could be due to whatever sort of phase discrepancy we have in our communication system. Okay, we got that. Okay, real operator applies itself, so get rid of that. So all we have is this cool thing here. Now, this cool thing, okay, that's great. We got this cool thing. I want to represent this in terms of I and Q. Okay, so first of all, apply the real operator. Now convert to IQ. So we have to do more trig identities. Trig identities. So what we want to do is, let's say we want to keep this and separate out that. So we got basically cos A plus B. Alrighty. So what's a trig identity for that? So trig. Okay. Trig identity for that, cos A plus B. Mu, 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 mu. There we go. Cos A plus B is going to be equal to cos A cos B. Minus shnikes. Sine A. So let's flip these suckers around. It doesn't really matter, okay? Sine B. 2 pi FC of t. All right. So this is actually quite powerful stuff. All right. So what this is at the end of the day, this is actually pretty powerful stuff. So what this says, okay, so here's the carrier, and here's the carrier. The I and Q component of this is this and this, okay? So this is actually, it makes sense for a number of reasons. So what we know, first of all, this guy and this guy are actually orthogonal to each other by 90 degrees. So what cosine and sine form is effectively an orthogonal basis function. They're not orthonormal yet. There actually is some theory behind, which we haven't covered yet, on how to make these two functions orthonormal, but they're orthogonal to each other, 90 degrees. And that's great, because what this does is it creates a coordinate system. And this is actually where we get the signal constellation diagrams from, right? But what this does, okay, if we now convert this into I and Q mappings, right? So if we go back to like the G of M of T, right? And we have X of this plus, right? This is equal to, so remember, folks, this is your in-phase component. And this is your quadrature component. So this is what gets mapped over, okay, to your signal constellation diagram. So what this is equal to is AC plus AC. You might wonder, where did the minus sign go? Well, remember, if you use Euler's relation on the complex exponential for the carrier frequency, it has a j. And so when you multiply j times j, it gives you a -1. And that's what happens to this guy there, right? So this, okay, what this does is, if you plot out your signal constellation according to I and Q, what you end up getting are these points. And what's actually really neat about these points is they form, okay, points into this plot, right? So another way of looking at it is in a vectorized format. What you get is AC cosine. Okay, that's your x coordinate, and then AC sine. It's absolutely beautiful. So let's take this another step. So for the BPSK that we talked about, right? And what we did is we had a mapping of 1 got mapped to 0 degrees, and we had a mapping of 0 to 180 degrees. And we said, oh, well, it looked like this, right? And that's a 1. And that's a 0. What happened is we can also have like a phase rotation, a constant phase rotation. That's where the theta naught comes in. So theoretically, what we could also have is something that looked like this for BPSK. Same BPSK, but let's say theta naught is equal to 20 degrees, or whatever it is equivalent in pi. What we would have is a 20-degree rotation, same distance away from the origin, and this would be the binary 1, and that would be the binary 0. But the overall phase rotation between binary 1 and binary 0 would still be 180 degrees. Beautiful. Beautiful. Seriously, this is absolutely fantastic. So this is I, and this is Q. Now, from here on in, we could do a lot of crazy stuff. So, like for instance, we can actually do some really cool things with respect to what happens if we have a coordinate system, right? Suppose we have I and Q, and we want to map now 2 bits per symbol. So first of all, let's say B, the number of bits, is equal to 2. That means we need to have 4 unique waveforms, so number of unique waveforms in order to be good. So what we would get, okay, if we choose a coordinate system, okay, for, let's say, 4 PSK, okay, so this 4, so the more generic expression, so this here is equal to M, right? What we would do, remember that all of these have a constant amplitude. So they're all the same distance away from the origin. So pardon my really poor drawing abilities. What we would have is we would have on this circle, suppose we would have 4 dots, and they would correspond to 4 points, each one with a different phase value from each other, right? This might have a specific phase. This might have a different phase. This might have an even more different phase, right? Now, this is all great, but what we want to do is, let's say we want to engineer something like a little bit more robust, like, you know, to have the phase values as distinct from one another such that there's no confusion at the receiver. So often what we do is we try and choose phase values, okay, in that IQ plane, right, in the in-phase and quadrature representation, such that it's like the phase difference is as different as possible between any two to minimize any confusion, right? Because if we go back to this guy, let's say we go back here, and let me illustrate. Let me draw an extreme case. But let's say we had this. Let's also start from the origin. Yeah, that's it. This is problematic. So remember many lectures ago when I started with phase modulation, BPSK, I was saying, oh boy, like try and create a detector that can differentiate this phase from this phase. You know, the human eye has a problem detecting phase. The receiver, not so much so. But if there's noise and there's distortion and stuff, let's say this phase value here, and you have this phase value here, right? they're both really close. So all you need is a little bit of error and you can mess things up. So again, there's motivation behind the following, which this is also for PSK, but we call it quadrature, okay? PSK. And this, what quadrature PSK does, is it's the maximum phase value from each other point. So first of all, let's say we have this theta naught, right? And then let's say 90 degrees it's this fella, okay? Then another 90 degrees is this fella. Then another 90 degrees is this fella. And then if you do another 90 degrees, you're back to the other fella. So quadrature PSK is very nice because this really separates out each one of these points, which could represent 0, 0, 0, also 0, 0. No, just kidding. 0, 1, 1, 1, 1, 0. Beautiful. Beautiful, absolutely beautiful. So that's what we would want to do, right? And that's I and Q. Now, we could take this even one step further. Nothing stops us from doing something like 8 PSK. You might say, what the hey is 8 PSK? This is what it is. And just FYI, if let's say this one here, let's say this theta naught is offset as much as like 45 degree, that we call this like, we have a name for this. This is pi over 4 QPSK. So this implies that we have essentially a 45 degree offset for all the points, right, with each other, but they're still 90 degrees separated from one another. So now 8 PSK, same unit circle or some sort of circle, same distance. Okie dokie. And let's cut this up like a pie. So let's say we have the following. They're all evenly spaced from one another. So we take basically 2 pi and we divide it by 8. Okay. So what we end up getting, shucks, what do we end up getting? So what you do is you would take 2 pi divided by 8. So what do you get? Pi over 4, right? So each one is separated by pi over 4, 45 degrees. I wish I drew better, but effectively that's what's happening here. And again, I'm engineering this to be evenly spaced because I want them to be as distinct as much as possible with each other. Because as you'll find out in a more advanced course in digital communications, what we're trying to do is avoid any sort of low-hanging fruit in terms of an error situation. So if 2 points are closer together than any other points, they actually will drive up the error probability. So we want to avoid that, right? So this is m equals 8, okay? Which means what's m equals 2 to the b? B is equal to 3. So each one of these points represents 3 bits, and so on and so forth. Okay. So if we so beautiful thing about PSK, modulation stays the same, frequency stays the same, but amplitude stays the same, the frequency stays the same, but the phase changes. Okay, and this is how we represent it in the IQ plane. So this is how we use the vectorization of a modulation scheme, and as you saw in the projects, this is how you see, when you have a clean signal and when you have a signal with an unpleasant amount of noise. Okay, So let's go back to the slides. I know I spent more time on this. Okay. Well, first let me save this before bad things happen. Boop. Perfect. Now I can go back to the slides. All right. Okay. So I just described that. And I just described that with vectorization. And there's some variations as well. Okay. So in this lecture, I spent probably more time talking about lecture 20 than 21. I just wanted a nice clean wrap up of lecture 20. So my apologies if I took a little bit of time with respect to FSK. I just wanted to make sure that it was kind of cleaned up before we went into PSK. With PSK, the big thing that I think is a key walkaway here is the fact that we can convert PSK modulation, okay, from that waveform representation. So this is something you'll definitely see in a more advanced comms course, like for instance, 4305, is the conversion from these waveforms into a vectorized diagram, which we can do with a digital waveform, okay? Because every TS seconds, this is a representation. This is a discrete representation. This is a discrete representation. So we can actually characterize it in the IQ plane. Analog, not as readily. Okay. So with that, that concludes lecture 21 of ECE3311 Principles of Communication Systems.